All right, everyone. Can you guys hear me well? Can you guys see the shared slides? Great. Um, Thanks a lot for coming. This is our eighth lecture on convex optimization, CS292F. We're going to be talking about stochastic subgradient methods today. Okay, so let's get the lecture started with a quick review of what we learned in the last lecture. So last lecture was devoted to mostly talking about detailed interpretations and for you guys to make sense of the algorithm that solves the composite non-smooth optimization problem with a smooth part and a non-smooth part called the proximal gradient descent. And to understand proximal gradient descent, we needed to go into more details about convex analysis and talk about functional conjugates, which allows us to calculate for any function f, the conjugate function f star of it. And with that, we were able to talk about the proximal map and the relationships to the Moreau envelope. And the proximal map gives the arc mean, and the Moreau envelope gives the objective function value. Okay, and then there's this Moreau decomposition of the identity map into the prox of f and the proximal map of f star of its f's conjugate. This holds more generally and can be thought of as a generalization to the projection to the orthogonal to an orthogonal subspace and its orthogonal complement. Okay, and then we talk about how the gradient of the Moreau envelope, which can be thought of as a smooth version of the non-smooth function f, is actually the Nesterov gradient map that we used previously. When talking about algorithmically how the proximal gradient descent can work. Okay, so this observation leads to two interpretations of the proximal point algorithm or proximal minimization algorithms that minimizes a non-smooth convex function f. Okay, by keep applying the proximal map from a given initialization until it converges. Okay, so this has the point of view of a fixed point iteration where we can write the proximal map to be in the operator sense to be the identity map plus the sub differential inverse. And this map, if you keep applying it, that gives you exactly the proximal point algorithm. And you can alternatively interpret it as first smoothing the function f into its Moreau envelope and using the property of the Moreau envelope, which says that the optimal solution is retained and also the optimal objective function values are also retained. That's why you can just do gradient descent on this, but solve a much slightly more difficult optimization problem in every iteration in order to evaluate this gradient of the Moreau envelope. Okay, so when we generalize the observation to the proximal gradient algorithm with two parts, with a smooth f and a non-smooth g, and the interpretation of the proximal gradient is similar, so you can do the quadratic approximation of the smooth part, which measurizes the entire objective function. But that doesn't solve the problem of the non-smooth term. So let's combine this with the idea of Moreau smoothing so that we can then run the gradient descent on the Moreau envelope of the locally linearized objective. And that allows us to construct a descent lemma that eventually leads to the optimal solution. Okay, so that was what we talked about last time. So today we're gonna come back to talking about algorithms. In particular, we'll start the first lecture on stochastic algorithms. So in which case there are randomness involved in your algorithm. Okay, so slowly we're getting more and more practical, and we'll see like how randomness can help us to solve a certain type of optimization problem faster than suppose you do not have so suppose you have to use you have access only to the gradient arc. Okay, in particular we'll be talking about stochastic gradient descent, and in particular we'll be talking about its convergence rate, its very different variants of SGD algorithms, and finally we'll talk about some interesting connection to early stopping and regularization, and so that you can maybe view stochastic gradient descent from a more like either like learning theoretic framework or statistical framework rather than viewing it as a purely an optimization tool. All right. Another thing is that for the purpose of this lecture, so even though I said stochastic gradient descent, so we'll not restrict ourselves to differentiable functions. So we can potentially like apply exactly the same thing to the subgradient method, but now with a stochastic subgradient. All right, let's get things started. So first, as always, let's talk about the algorithm. So the algorithm is usually quite simple in this course. So think about the following optimization problem that is a summation of m different terms. So you can think about this fi. Each one of them is the loss function corresponding to the ith data point, and m is the total number of data points you have. And we're optimizing over the parameter of the model. So so eventually we're trying to find the so-called empirical risk minimization. Empirical risk minimizer. Okay. Example of these include fi of x to be, say, the square loss y minus x transpose, and then phi square, where phi is a feature vector. This is a label, and then we're doing the regression problem with coefficient x. Yeah, so notice that in machine learning literature, it is common to use I guess x to denote the x to denote the data vector, the feature vector, and use maybe theta to denote the theta to denote the coefficient, and then use xi to denote the feature vector. So in order to keep things generic, like sometimes we use this alternative notation with x to use x to denote the argument that we're optimizing over. Yeah, just don't get confused when you see x. So sometimes there x is a parameter vector that we're optimizing over. In other cases, xi, like we might be referring to the fixed data point that are passed into the optimization problem as in order to construct this criteria function to be optimized. Okay, so suppose we want to apply the gradient descent method to this. So in every iteration, we need to evaluate the gradient, which involves but after it's changing the order of summation and taking the gradient, which involves taking the gradient of every data point and then add everything up. And after we complete the full data pass, we calculate the gradient, normalize it according to this normalization factor, and then move along the direction of the negative gradient by a little bit. With a carefully chosen step sizes to take, or we can alternatively just do backtracking. Okay. In comparison, stochastic gradient descent, like it's in some sense it's more adaptive. It's also known as incremental gradient methods for minimizing functions of this form. That when the objective function can actually be decomposed into multiple components. Specifically in SGD, we somehow like pick this index ik. In case iteration, let's pick this index ik, sometimes randomly, or we can pick it using other techniques. Then move along the line of just that direction rather than going over the entire data set with every update to the parameter. You can see that comparing to the gradient descent, stochastic gradient descent updates the parameters a lot more times. So each iteration costs significantly less, but it is not really moving towards the gradient direction of the objective function. So it may not lead to an improvement on the objective function, function level. Okay. So let's talk about how we choose this index ik in every iteration. So there are two popular approaches. The first approach is a randomized rule. So you basically pick each IID at random, uniformly at random. And once you pick something, you move along the direction given by that gradient corresponds to that data point to put it back, right? So each time you are sampling from the same distribution of index 1 to m. There are other rules. For instance, the cyclic stochastic gradient descent, cyclic like incremental gradient descent, essentially goes over the data set in the same order in every iteration, right? So you go from the first one to the last one, and then you keep cycle through the data sets. And after every every cycle, you go over each data point exactly once, and that's a method. That's a legitimate method that people have tried before, have implemented, and they are like convergence guarantee that's stated for this alternative rule of choosing these indices. Okay, there's like one more rule called cyclic reshuffle. So this is typically the rules that's used most common in practice. So before every like you shuffle your data before going through the data set one by one. Okay, so you can think about this as something like in between the randomized rule and the cyclic rule. The randomness is coming from shuffling, and in every in every data pass, you're going through a different like randomly selected order. Okay, so it turns out that the last one is the most commonly used version of the stochastic gradient method in practice due to some system benefit, and it was actually shown formally that this reshuffling leads to faster convergence than the naive cyclic rule. Okay. Okay. But for today, we're going to be sticking with the randomized rule for the following reason. Okay, so when you pick this index uniformly at random, so the very nice property of that is that when you take the expectation over the gradient, stochastic gradient that you sampled, you actually recover the full gradient. Okay, so this is easy to see. So notice that this expectation is taken only over the randomness of your algorithm, in which you are selecting this index ik uniformly at random. So you can clearly see that if you just apply the definition of this expectation, so that will be the sum of the probability of choosing each I, and then you have a gradient of fi x, and that is equal to the full gradient. Okay. So every iteration of stochastic gradient descent requires only calculating the gradient with respect to one data point. Therefore, it is independent to the size of the data. And so that can be significant when you are in the big data regime and you are dealing with millions and even billions of data points that are not even stored in the same location. So in this case, using SGD can lead to a significant savings in your in both optimization and in terms of the communication cost, like among servers when everything's distributed. So let's give an example of stochastic gradient descent using our familiar example of linear logistic regression. Okay, so in linear logistic regression, let's say that we have data points that's with a p-dimensional feature, and then the labels either 0 or 1. So it is a logistic regression for binary classification problems. Okay, so recall that this logistic loss is a surrogate loss of 0, 1 loss, and it is convex. You can clearly see that because the first term is a linear function in beta, and the second term is log sum exponential with this term replaced with an affine input. Therefore, the whole thing is convex. Okay, so the gradient of the logistic loss of this form has an interesting structure, right? So if you take the gradient, the first term gives you just y y times x, right? And the second term, notice that y is a scalar, and the second term gives you actually gives you the soft prediction of your logistic regression classifier at data point xi when beta is given to you by the current iterate. So pi here, pi beta is equal to 1/1 plus e to the power of minus xi transpose beta. Okay, so this is so notice that this is this gives you a probability distribution. So it tries to predict the probability of observing y given xi, okay, on the data. So let's check this for people who are like not too familiar with logistic regression. So let's say that this score function xi transpose beta is hugely positive. So that means that our algorithm says that this is overwhelmingly, I have overwhelming confidence that this data point I'm going to predict the y to be 1, right? In this case, this probability is close to 1. Right? Because as this score function gets larger, this exponential term gets exponentially close to 0. On the other hand, like suppose this xi transpose beta becomes hugely negative, that means that we have strong evidence to believe based on the current coefficient beta that the true label is 0. In which case, this probability will converge to 0 very quickly since the since the denominator goes to infinity very quickly, it explodes exponentially. Okay, so that makes this gradient very interpretable because it's just the true label minus the predicted soft label, and then depending on their discrepancy, are moving towards the direction that's pointed by our data point xi. Okay, so just a little bit of insight for those who are not familiar with machine learning. Okay, so the point here is that the gradient calculation itself requires us to go through the entire data set one by one and then calculate this, make prediction for every data point, and then construct the gradient. This is like not okay if n is huge, right? So large scale logistic regression is the underlying technique that everybody is using. Like for instance, Google's using this for serving its advertisement, and by collecting features of users, features of the advertisement, and all the news and everything, and it is really their bread and butter. So being able to solve this at scale is critical to a lot of the applications of logistic regression. Okay. On the other hand, like suppose we do an SGD as update, right? That requires us only to pick a random data point and then update the parameter. So it takes only like computation proportional to the dimensionality of the features. And in fact, it can even be faster. So in many cases, when the feature vector x is sparse, this means that there are only like a small number of non-zero elements in X. If you look at the gradient here, the gradient is also, the stochastic gradient is also S sparse, which means that instead of taking order of P computation in every iteration, you take on average, in every iteration, you take on average NNZ, the number of non-zero elements of the entire data matrix, divided by n. So this is average per update cost by running stochastic gradient descent for one iteration. Okay, so therefore running many iterations becomes significantly possible. Become really have a reasonable computation cost, and people can even afford to do that on smartphones and edge devices. Like you can even run stochastic gradient descent on the IoT devices that you host at home. Okay, so so let's look at this classic picture of the comparison between SGD and the full gradient descent on the previous problem. So let's make it simple so we can visualize it. Let's choose a two-dimensional feature with p equals to 2, and well, let's take on a n to the 10. So there are a total of 10 data points, and then again this figure draws the feature dimension x1 and x2. Okay, x1 and x2. Okay, so these contours are again equipotential contours. So you can think about what is enclosed in these contours, the level set, the level sets of the convex objective function that were minimized. Okay, as a result, this star is a global optimal solution, and both algorithms start from the initialization here, and when we take the batch gradient descent for say 20, 30 iterations, it gets to the optimal solution pretty quickly. And if we take the stochastic gradient descent for 20, 30 iterations, you'll see that it jumps around more randomly. But it is moving towards the direction that is towards the global optimal solution in general. Okay, it takes a little bit of jump around, and it is extremely fast at the beginning, but then it struggles when you hit the region where it is ambiguous which direction you should move, and then it takes a little bit more time for you to actually converge to the high a solution with high numerical precision. Let's talk about how do we typically choose step sizes in stochastic gradient descent. Okay, so in general, to guarantee convergence for SGD, just like the subgradient methods, it requires us to use step sizes that goes to 0 as k gets larger. So specifically, a particular choice can be tk over equals to 1 over k, or tk equals to say 1 over square root of k, or something between. Okay, so notice that like we talk about the diminishing step sizes that's square summable but not summable. So that's the same type of diminishing step sizes that we need to guarantee convergence for SGD, as we will see later. Okay, so why don't we fix step sizes? Part of the reason is that if we just fix the step sizes, then it becomes very difficult for us to, in some sense, average out the noise. So let's compare two a specific algorithm to see this for sure. So let's on top we have this cyclic rule for stochastic gradient descent, and let's take that for m iterations. So in this case, there's no stochasticity involved, and every epoch involves going over the entire data set. Okay, so if you look at a fixed step size that looks like this, then we are essentially evaluating the gradient of ith data point at a parameter like k plus I minus 1. So at the case we are evaluating the first one where we move towards that direction, and then on the second step we keep updating our parameters while updating the index of which data point to choose next. Meanwhile, we know that suppose we do the full gradient descent, then the input to this gradient calculation remains for all data points at this location xk. Okay, so if this is the right direction to go to go towards, then it is unlikely that doing this will actually move anywhere that's near or what this direction is going. Like suppose we take the two differences of the update direction. So ideally, like after you take m steps and m is huge, we should expect that these two directions should be yeah pretty similar. We should expect that that doing this will get us closer to the optimal solution. However, if just do the pointwise differences, we see that we see that there could be systematic drift between these two that makes that makes the cyclic rule like moving towards the direction that's unclear which way it's gonna go. So in general, even if you start at the location x optimal, right? In which case the second term becomes 0, but the first term will still jump around, and then it may like diverge up to a point that's given to you by the size of the step size. Okay. So how quickly does the stochastic gradient descent converge comparing to its full batch gradient counterpart? Okay, so we've learned that for if all we want to assume is the function is convex and nothing else, we've shown from the lecture before the last one that the subgradient method, if you move along the direction of the subgradient, you'll get the 1 over square root of k convergence. Yeah, or 1 over epsilon square iteration complexity. And suppose you assume f is differentiable and strongly smooth or having Lipschitz gradient, then you can improve this rate to order of 1 over k, 1 over epsilon. But it turned out for stochastic gradient method, using diminishing step sizes, we can actually get something that's very similar to what you would have gotten for the subgradient method. So the expected objective function value of the case iteration converges with also the rate of 1 over square root of k, but with an additional logarithmic factor that sits on top. Okay, so this is a mild loss comparing to this, right? Notice that we are solving the same family of functions, so as long as you can approximate the gradient somehow more efficiently, then this is saying that the total number of iterations that you converge is about the same. Like it blows up only by a logarithmic factor. Okay, so what if we add smoothness to our objective? So what if in addition to this, f is also smooth? Its gradient is Lipschitz. So unfortunately, that doesn't actually improve the convergence like almost at all. So even if we assume f is smooth, we can still only get the 1 over square root of k convergence, and you can get rid of this additional log k factor if you look at the result of yeah, I forgot whether it is a Shamir or Zhang paper, but Shamir and Zhang paper talk about a lower bound and how assuming just Lipschitz gradient is not actually going to help you in general with solving this family of functions faster. Okay, so so notice that in the subgradient methods that we talk about, this is slightly different. This is a slightly different result comparing to the result that we learned 2 lectures before. Okay, so just a reminder, we proved the version of the subgradient method result of f k best minus f star. Okay, but here this is saying that the last iteration also satisfies the same quantity, same convergence bound. This is not something that we talked about, but it is true as well. The proof is a little bit more involved, so we're not covering it in this class. So so it turns out that if we use a slightly different rule here, instead of talking about the last iterate, suppose suppose we do a little bit be a little bit more clever and then construct alternative updates that you can get from the entire sequence of iterates. In particular, we can take the average, which is 1 over k sum over I from 1 to k x I. Okay, if you do this, then you can already get rid of the log k factor without even assuming smoothness. That is a reason why like the smoothness doesn't quite help, like for some reason for the stochastic gradient descent to achieve a faster rate. Now what if we in addition assume that the function is strongly convex? Right, so so we know that when the function is strongly convex and smooth, then we can come up with a proof of the gradient descent method and also accelerated gradient descent method, in which case it converges linearly. Okay, so this corresponds to iteration complexity of log 1 over epsilon. On the other hand, like strong convexity also doesn't seem to help gradient descent, a stochastic version of the gradient descent too strongly. Like we do get some improvements, right? So after assuming that the function f is strongly convex, we can improve the 1 over square root of k to 1 over k. But this is an exponential loss comparing to the version where you are able to evaluate the exact gradient. Okay, so so this is part of the reason why the stochastic gradient style methods struggle within the neighborhood of the global optimal solution. And even with the strongest assumption that got added to the problem, we're not able to, in general, improve the convergence to beyond sublinear convergence. Okay, so then what are the tricks that people are using in practice to improve SGD? Since this is an algorithm that has very many desirable properties. So one of the things that people use quite often is a so-called mini batching. Okay, so notice that the version of the SGD that we talked about selects a single data point and then evaluate the gradient there. So alternatively, you can construct the stochastic gradient slightly differently, right? So you can construct the update by randomly selecting a subset of size B. Right, so provided that the size B, the parameter B is significantly smaller than the size of the entire data, then you can still get the reasonable system benefit out of running SGD over the gradient descent. Okay, so clearly, since this subset is randomly selected, we can show that this direction that we are updating satisfies the unbiasedness condition that takes the expectation over the randomness of selecting the subset. It recovers the full gradient. Okay, but what's the benefit? So when you do mini batches, it actually reduces the variance of the gradient by a factor of 1 over d. Okay, since so you cannot directly see this from like statistical estimation with IID data, because the summation of these um, um, data points are not actually IID. But if you use statistics to calculate the variance, you can see that like when you do the mini batch, then the variance of 1 over b sum of fi when I in this random ik is um, 1 over b times the variance of individual fi. This is 1%. Okay. If you construct your mini batch by sample with replacement and then just average things out, then you get equal sign here. Okay. So so what's the computational benefit of this? So let's just do the asymptotic calculation with a big O notation. So suppose you run the full gradient descent with the data set of size n with number of features being p. So in this large scale logistic regression problem, this is how much it takes to update the parameter once. And suppose you use a mini batch, then instead of n, you can replace n by b. Okay, and finally, like if you just do the standard stochastic gradient update with b equals to 1, then you depend only on the dimension and completely independent to the data set of the data. Okay, so like the number of iterations actually matter. As we have seen previously, the convergence of the method depends on the many iterations that's being offered by STD, right? So as k gets larger, we get closer to the optimal solution. Like suppose we do mini batch, then that's taking away the number of iterations. Like what's the benefit of that? And we have a smaller number of iterations. We have b times smaller number of iterations. If we want to equalize the total number of computational costs in terms of the number of flops. Okay, so let's maybe run all algorithms for a fixed number of iterations and see what's going on. So clearly, if we run the algorithm for 50 iterations of the logistic regression example, but now like let's use a larger data set, we see that gradient descent converge quickly, and converge like in 10 steps. If you increase the size of the mini batch from 1 to 10 to 100, then you do see some improvement in the number of iterations that are needed to converge to a reasonable solution. Okay, and it in some sense stabilizes around the region that are still having a gap from the from that of the full gradient descent. Okay, but this plot can be deceiving because every iteration is significantly more complex and more costly in full gradient descent than in mini batch version of the gradient descent compared to the stochastic gradient descent. Let's maybe rescale the horizontal axis of this figure a little bit by making it the total number of incremental gradient calculations, by making it the total number of floating point computations. If you do that, you see that the fastest suddenly becomes the stochastic gradient descent with batch size equals to 1. Okay, at least it gets you very quickly down slope with the smallest number of flops count. Even though it doesn't like if you keep running this, it may like taper off. But it is really the fastest algorithm that gets you that gets you downhill. Notice that the horizontal axis is now in logarithmic scale, so this is like somewhat like so it's unclear whether it's going to go this way or it's going to go this way, but it will oscillate a lot as you get closer to the optimal solution. Okay. So So let's make that point clearer. Suppose we just now make it the semi-log plot on the other direction, right? So let's compare the suboptimality gap. So this is the difference between the solution that you get in the case iteration and that of the optimal solution. Okay, so if you look at this, then gradient descent, like we know that this is a strongly convex optimization problem with this additional quadratic regularization term. So we should expect this to converge linearly. Indeed, gradient descent converges linearly with a very nicely looking like linear line on this semi-log plot. On the other hand, like all the other algorithms seems to struggle like significantly on the surface without getting it even below 10 to the power minus 3. Okay, so when you see figures like this in when reading papers, you should you should notice the caveats because these are the same set of experiments and these are the same algorithms that we're comparing, but just depending on like how we are presenting the experiments, the intuitive conclusion that you get might be vastly different. So at the end of the day, what really matters is that which algorithm can get you to your desired suboptimality fastest. So suppose your desired optimality is here, then the stochastic gradient descent without mini batching is actually the fastest. And maybe that's a good trade-off in terms of the time and accuracy of your optimization. Maybe the entire region from here to here are regions where you are overfitting to your training data. So getting a more accurate solution to your training data might not actually be over optimizing. So getting a lower empirical error on your training data may or may not lead to better accuracy on the future data when the samples are drawn from the same distribution but not necessarily the same examples. So we'll take a break and we'll resume at 1:50 when we can start talking about the proofs of the convergence of the subgradient method. Meanwhile, please leave your questions and comments and everything in the group chat, and I'll respond to that at the beginning of the second half.
Hi, can I ask a question that may be a little bit trivial?
Yeah, go ahead, please.
Yeah, so if you can go to like the previous 3 or 4 pages, and then there's a figure showing
Which one?
those 4. And yeah, so you mentioned there is like a suboptimality between the stochastic method and the full batch full batch gradient the full method. I just want to know that since this picture shows that you all use the fixed step size, I was wondering if you use some kind of the adaptive step size, will that suboptimality be fixed or not?
Yeah, excellent question. So you'll see that in the proof. So yes, if you use a diminishing step size, you'll see that eventually converges to the optimal solution. It's like by diminishing step sizes, you are doing something similar to simulated annealing. So you are like adding a lot of the randomness together and then average them out. So if you use a diminishing sequence of diminishing step sizes, you eventually converge to the optimal solution. In probability, in expectation, and if you want more technicality, you can also show it converge with, I guess, almost surely.
Oh, that's nice. Thanks.
Yep. Yeah. Thanks for the question. So let's resume. So I believe now everybody's like happy with what the algorithm looks like, how it behaves intuitively on this example of like logistic regression. So let's move on to understand how these algorithms actually converge and what motivates us to select these sequences of learning rate that's summable, that's not summable, but needs to be square summable. Okay, so let's move to the written notes so that we can make it slower and everybody will understand this better. Okay, so again, the algorithm that we want to analyze now is the stochastic subgradient method. So for over T1, okay, update, sorry, okay, technical K, then update X, xk plus 1 equals to xk minus some step size tk with an approximation of the one of the subgradient. Okay, so I can call this gk. Okay, and we're making 2 assumptions about the subgradient. So the first assumption is that the conditional expectation of this subgradient estimator given xk is unbiased. So it's actually gonna give me something gk where gk is a subgradient of f at xk. Okay. And the second assumption is that gk is has bounded variance. Okay, so I guess the square given xk is smaller than say sigma square. So notice that this is a differences in the vector space. So there might be a dimension dependence that's hidden here if the noise is added to every coordinate. But in the cases when this G when this stochastic approximation is bounded on its own, then you can claim that this is dimension independent. Okay. Yeah, actually, there's a third assumption that we need to assume, just like in the standard subgradient method, which we without assuming differentiability, and we have to assume something to make the convergence concrete. So we'll assume that the function itself is G Lipschitz, which essentially is saying that all subgradient satisfies that the two norms are bounded by G. Okay, with these assumptions, so let's move on to try to analyze this algorithm. So we'll make use of the same sequences of argument as we analyze the non-stochastic subgradient method. So and you'll see like the proof is going to be very similar to that. Let's consider just update from x to x plus used by running one iteration of the stochastic subgradient method. Okay, so let's again compare to that of the optimal solution, and then apply the definition of the algorithm. Okay, let's expand that. So let's group this x, the previous iteration of x, with x stars for the interest of constructing a telescoping structure in the inequality. And then there's this cross term plus the other square term that depends only on the approximate subgradient. Okay, now let's take the conditional expectation on both sides by conditioning on x, right? So whenever we take expectation, try to ask yourself like, what is random? What is this expectation taking over? So in this case, we know that this expectation is taken only over the randomness of your algorithm in selecting the in randomizing the gradients, okay, so in subgradients. So it is a randomness over G hat. So anything that depends on G hat will have to be randomized out, and everything that depends only on X will be kept as a constant without doing anything. So the left hand side clearly depends on G hat. So we can write the conditional expectation of x plus minus x star squared given x is equal to, this term is independent to your updates. So let's just write it down. And the third term, so notice that it's a product of two things. And this one depends. This one is independent to the randomness that we're taking expectation over, and this one depends on the randomness, so that we can push this expectation inside this inner product, and get 2t expectation of G hat given x transpose and x minus x star, and plus t square expectation of G hat square given x. Okay. So so with this, we can already apply our assumption 1 on this quantity, right? So let's do that. So x minus x star square minus 2t. So this is actually just the subgradient without the additional noise, without the additional randomness. How about the last term? So notice that this is what we assume, right? This is what we assume. We can add and subtract gk. we can add and subtract gk, so that we can get plus t square and g square plus the expectation of g hat minus g square given x, and then apply the assumption 2. Okay. So this is y 1 and 2. Okay. Can anyone tell me like why where did the cross term go? So when we add and subtract g, so there should be a cross term in the form of I guess 2g transpose g minus g, right? To get this given x. So this term is actually 0, right? Because by assumption number 1, then the expectation of g hat is equal to g, and this g is fixed given x. Therefore, like this cross term actually goes to 0. Actually is 0, so we don't need to worry about it. Okay, so now apply assumption number 2. We can replace this with plus sigma square. All right, so that simplifies things a little bit, and now now let's apply the definition of convexity. So so just like before, so now that we have gotten rid of the stochasticity in the second term, we can apply the definition of subgradient and the fact that the function f is convex, and then bound the second term with and well, then by the additional condition on the Lipschitz gradient, so by assumption 3, so we get g square plus sigma square. Okay, so that gives us something that very much resembles what we had with a non-stochastic subgradient method. Now take full expectation. Take expectation over everything on both sides, and that gives us the expectation of x star x plus minus x star square. So notice that we don't have any conditioning anymore. So since x depends on all the iterates that's before it, so now I'm getting rid of all the complicated randomness that we don't know how to deal with. Minus 2t. So notice that f of x is also random here. So so this will be f expectation of fx minus f star plus the last term. The last term at least is constant.
Excuse me, Professor?
Yes.
Are you writing out of boundary and we can't see the notes?
Interesting. Okay. Can you guys see it now? Can you guys see it now? Okay, yeah, so yeah, I think it's because my second monitor has a vertical pixels that are smaller than that of my iPad. So hence the issue. Like, sorry, thanks for pointing it out. So now I move it to the bigger monitor, then everything seems right now. since people have not been able to see the last line, so in the last line, I'm basically taking the full expectation over everything on both the left-hand side and right-hand side of the equation that I had, inequality that I had before. So that takes over the randomness of x. Okay, and on the right-hand side, I'm just propagating this this through, and now we have an equation that we can telescope. Okay, so let's move to the next page and then actually telescope it. Okay, so so let's telescope with k from 1 to k. Okay. So we have expectation of x2 minus x star smaller than expectation of x1 minus x star at the initial point. So if your initialization is random, you can also drop this expectation. Minus 2 step size of the first iterate, expectation of f of x1 minus f star plus t1 g squared plus sigma square, right? So on the second step, just applying that, you get x3 minus x star smaller than x2 minus x star minus 2t2 expectation of fx2 minus f star plus t2 square g square plus sigma square. Let's sum that all the way to the end where we get xk plus 1 minus x star smaller than the expectation of xk minus x star minus 2t k e of fxk minus f star plus tk square g square plus sigma square. So let's add everything up. So as we add things up, we see that a lot of things got canceled. So this term got canceled there, this term got canceled there, and then we can move we can move the summation that has something to do with the suboptimality gap to the left hand side, and then move everything else to the right hand side. And that gives us 2 times the sum of I from 1 to k ti and expectation of f xi minus f star. Okay, this is what you get on the left hand side, and this is smaller than your initial points. Minus something that's positive. And I guess plus everything else that's trailing. 1 to k with a constant multiplier towards the end. Okay, so once we get this, there are 2 things that we can do. So we can choose this step size carefully. So first of all, suppose we can lower bound. Strategy 1. Okay, so notice that the left hand side is of the form of summation of ai bi, right? And we wanted to get a lower bound of this summation ai bi. So we can bound this either by the minimum I of A multiply with the sum of BI, or we can lower bound this with minimum I of BI multiply with the sum of AI. We can do either these two things when AI BI are both non-negative, right? So these are both valid lower bounds of the left-hand side. So if we do the first approach, then strategy one, so we can group the summation of this TI together and then get the sum of I from 1 to K TI, and then lower bound the above with a minimum over all I of this suboptimality gap. Okay, so this is essentially the best iterate during the best iterate during the entire optimization process, and this is smaller than I guess the location of your initialization. Yeah, and if we move this to the other side, we get 2 times sum of I from 1 to K TI, right? So this is saying that as long as we choose a learning rate appropriately such that it is square summable, this becomes a constant. And this becomes not summable, this goes to infinity, and this is bounded by positive infinity, then we get something that converges. Okay, so that would reproduce the claim that we had in the on the previous slide. So the second strategy. The second strategy would be lower bound the left-hand side in the other way around, right? So we can lower bound the left-hand side with a minimum of I of TI, and then we will end up having the sum of the expected f xi minus f star. Notice that we're summing k different things, so we can so yeah, let me write everything in full. Okay, so that gives us something that's slightly stronger if we divide both sides by k. Divide by k multiply with a minimum of TI. Okay, so once we do that, we get the 1 over k, 1 to k, expectation of fxi minus f star. So notice that this is an average suboptimality throughout the updates. So this is smaller than this term plus divided by k times the minimum TI. So let's now choose this TI appropriately. So let's choose TI to be a constant. Now that we know that this is a total number of k iterations that we want to run. So let's choose TI to be 1 over square root of k. Okay. So if we do that, the minimum is going to be just the same as k times 1 over square root of k. So that will give you square root of k. And on the numerator, we get the boundedness of the space square plus, now that everything is 1 over square root of k, square of that will be 1 over k, but we're summing over k different things, so in total it adds up to 1. So we get g squared plus sigma square on the, yeah, I think I missed the factor of 2 here. I can, add this 2 here. And that gives us that gives us a bound on something that's slightly stronger than the one that we had, because the average is always larger than the minimum, right? The average is larger than the minimum. Therefore, we are bounding the left-hand side with the left-hand side is something stronger that we're able to control with essentially the same bound. Okay. So let's go back to this. Let's go back to the slides, and then so we've just proven the convergence of stochastic subgradient method, and shows that its rate is order of 1 over square root of k under these conditions. So now notice that in the standard gradient descent, we also talk about like how the methods converge for non-convex optimization, right? So under this assumption that the function is satisfy L Lipschitz gradient or L strongly smooth, with a particular choice of fixed learning rate, fixed step size is 1 over L. So so how does that like argument follow through in the stochastic version? So the statement is here. So on the left hand side we have the average. I guess instead of suboptimality, now everything is non-convex. All we can say is a computational guarantee about the convergence to the stationary point, and this is a measure of how far away that you are from the stationary point by measuring by measuring the first order optimality condition. Okay, so the difference is that you now have an expectation here. And on the right hand side, you see that we can get a bound of 1 over square root of k again, comparing to the 1 over k convergence of that of the gradient descent. Okay, so let's be more concrete and then work this out as well, and you will see how the descent lemma would be different when you add stochasticity, and that might be a little bit more informative. Okay, so yeah, before that, if we take a step back and then look at the whole proof, then everything look at the whole proof of the subgradient descent and compare that to the stochastic subgradient descent that we talked about just now. We notice that they are more or less the same argument, except that we need to be careful in taking expectations and applying this these additional conditions. Okay, and the real key difference in the final bound that when we end up getting is that here we have an additional sigma square. But what if sigma square is just on the same order as this g square? Then this really means that we're not losing much. This really means that by introducing stochasticity, we managed to speed up the convergence of the algorithm without losing too much in terms of the convergence rate. Because even if this sigma is chosen to be 0, like we still have this 1 over square root rate. We still have to set the learning rate to be a diminishing set of learning rates such that the summation of the sum of the squares of the learning rate becomes a bounded number. Okay, so that's the intuition behind why adding stochasticity isn't really making isn't really making the subgradient method convergence significantly slower. That also says that in practice, maybe it doesn't make sense to run subgradient descent at all when stochastic subgradient descent is something that you can get away with. Okay, so now let's move to analyzing the non-convex case. Non-convex case. Okay, assumption. Let's assume that the function f is L smooth. Okay, and we'll also have to assume everything else, right? So so in particular, this g hat, conditional expectation of this g hat at any given x is equal to the gradient of f of x, right? So L smooth implies that this function needs to be differentiable, right? So now we can use the gradient rather than the subgradient, and that's convenient because for non-convex functions, subgradients might not exist, and we cannot really do anything in that case. Okay, so let's work with the differentiable functions, and the second condition is that the variance is smaller than sigma squared. Okay, so under these two conditions, let's maybe work out an analogy of the descent lemma that we had from gradient descent. Okay, so recall that in the proof of the descent lemma, so we start off with something like a Taylor expansion of the function at the current iteration. So so we apply the definition of L smoothness. We can majorize the function by by a quadratic function that's constructed from this linear approximation, and then add this additional quadratic term to that, which gives rise to plus right by the L smoothness condition, we can write this. So you guys have proven this in the homework 1. Now let's take the conditional expectation on both sides by conditioning on x again. So we can fx is a constant, now that x is conditioned down. Okay, so by applying the update rule, we know that x star minus x is the negative gradient direction. The approximate gradient direction. So we have t g hat. So we're moving towards the negative g hat direction. Gradient of f, but now we're taking the expectation here. So let's take the expectation here. Plus half L t square, then g hat expectation x. Right. So all we did was to apply the update rule and then apply the conditional expectation. And as before, we can write this as minus t. If we evaluate the gradient, we'll get that the conditional expectation of g hat is actually the gradient. And then using the same decomposition and the same fact that the cross term is actually 0, we get by applying the variance bound, we get gradient of fx plus sigma squared. Okay. So now let's group the terms with a gradient together. So this is the same steps that we use when analyzing the gradient descent. So the only difference when we introduce the stochasticity now is that there's a trailing term that depends on the variance that depends on the sigma square. So this term is new for SGD. Okay, but that's okay. And the reason why that's okay is because you now have a t-square term here. So as long as you choose diminishing step sizes, and then everything should be fine, right? So you can start by so let's maybe simplify this term a little bit by making the assumption that for all steps we are choosing learning rates that are strictly smaller than half 1 over L, and that gives us we can replace one of the t in this t-square term to cancel out with this L. So that gives us t minus half L multiplied with 1 over L multiplied with t. These two got canceled out, and the gradient of fx square. And this whole thing is half t plus 2L t squared sigma squared. Now, finally, take expectation on both sides. So we can get rid of the conditioning. Then we have x plus smaller than the expectation of fx. Notice that the reason why we need to take the expectation is because fx is random, right? X is random, it's coming from all the iterates before this point. And each one of the iterates is random, so you end up having a very complicated randomness that got added together. Minus half t expected square norm of the gradient at this location. This is something that we want to bound, plus half L t squared. Okay, so with this, we can now telescope after we move the expected gradient norm term to the left-hand side, and then we can telescope and then cancel out the iterates of the expected objective function value. So I'm gonna skip the steps. I'm gonna skip the steps a little bit. So we'll get I from 1 to k. So you will have tk, and then the expected gradient of f I ti. You have ti, and then the expectation of the gradient of fxi norm on the left-hand side, and on the right-hand side, you will have I guess yeah, I think you have a factor of 2 here. On the right-hand side, you get the objective function value of the first iterate minus the objective function value of the k plus first iterate. plus 2 L sigma square and sum of I from 1 to k ti squared. Okay, so after we telescope over the iterates, so this is the inequality that we get. So again, like there are these two strategies that we can use to deal with the terms that's on the left hand side. So for now, let's maybe just take the constant learning rate for this case. Let's take the constant learning rate to be 1 over square root of k. Okay, so if we do that, the left hand side becomes half of the square root of k, and then it becomes half. Now let's be a little bit more clear here. So 2 square root of k1, and then sum of I from 1 to k. Minus f star. So because we can always lower bound this term with f star, plus half L sigma square. So now that we have chosen Ti to be a fixed learning rate 1 over square root of k, the sum of this will become 1. Okay, now it remains to divide both sides by square root of k is also over 2. Okay, so you get 1 over k divided by square root of k. Okay, so that completes the proof that of the result that we talked about in the slides. Okay, so if we compare to the gradient descent, we see that the reason why we're getting the square root of k over here rather than rather than k in the denominator is precisely because that now that there is this additional trailing term that involves that involves sigma square that we have to deal with by annealing and by choosing the learning rate to be really small. Okay, so I guess the high level story of these convergence proofs are that so you wanted to choose the learning rate to be as large as possible so that you converge quickly. You move more significant advances in every iteration. But on the other hand, like you want to be careful so that things do not diverge, right? So when we do this kind of analysis, it becomes clear to us what is a reasonable choice of the learning rates that allows us to always make improvement. So maybe the improvement is only in expectation, but we want to make sure that at least after we average out all the possible randomness, we are actually making improvements, and that's what the descent lemma in the non-convex and smooth optimization is telling us. So unfortunately, we don't get back the same rate as that of the learning rate, but that's that of the gradient descent when we have access to the full gradient. But that's just the way it is in life. Yeah. So there's a question about what is f star. Yeah, thanks for that question, and it looks like Kai-Chi has already answered. So f star is a optimal criterion value. So it is smaller than any other xk. Therefore, the expectation of f xk minus f star is always positive. or at least always non-negative. Okay. Okay, so we'll skip the part with establishing the 1/k convergence rate for strongly convex and G Lipschitz functions. So notice that we don't even need we notice that we don't even need this the gradient Lipschitz. We don't need smoothness. All we need is strong convexity and Lipschitzness of the function for us to establish this 1/t rate, 1/k rate. So again, we'll talk about this when we get to online learning, and that will allow us to state this result as a simple corollary. Okay, so there's one more thing that I'd like to talk about this convergence, right? So in the so we didn't actually say anything about x to the k, right? So the last iterate, like we didn't say anything about the convergence of the last iterate. Instead, in the two strategies, in the first strategy, we end up getting a guarantee for the best possible solution that's among all the iterate. Okay, so this is okay in the context of doing gradient descent, because in the gradient descent you can actually evaluate the objective function value for every single iterate and then keep track of the one that minimizes this online, right? It doesn't really take any additional effort since you are evaluating the full gradient in every iteration. So what additional cost that can give you if you do if you simply keep track of the minimum objective function value. But that's not really the case for stochastic gradient descent. For stochastic gradient descent, you can't afford to evaluate this for every iteration, right? Because every iteration, if you evaluate the objective function value, it will take a computation that's proportional to n, right? So this style of guarantee, like even though it follows the same principle as the gradient descent, it doesn't really tell us much about what we can say on the concrete parameter that we end up getting, right? So there are solutions to this problem. So we've seen that in strategy 2, we've derived something that's a little bit stronger than what we proved here on the left hand side in terms of the average suboptimality over all the iterates. So we'll see how that can help us to actually construct a guarantee that we can actually concretely calculate, okay, without incurring additional computation. So notice that we can use a very computationally online update rule to keep track of the so-called online averages. So online averages are essentially the average of x of so it is the average of the solutions that you end up getting so far. Okay, so you can compute this online using like what the optimizers call the Polyakh-Rupert averaging, but I am sure this idea is around for a lot longer than what they propose this for the context of optimization. So from the previous theorem where we can establish a bound on the on the average of the expected suboptimality, I from 1 to k minus f star. Okay. We have an upper bound of this sort that looks like 1/√of k, right? So this was our result when we applied the strategy 2. So can anyone tell me why does this imply a result of the convergence guarantee of this x bar estimate or of this x bar solution? Yeah, just a quick quiz to you guys. Can anyone who has an answer to this either say it or post it in a group chat? There's a first answer that from Alex saying that they are equal. No, they're not actually equal. So notice that the expectation is on the parameter x when we come up with x bar, and the expectation is on the suboptimality. Yeah, the second answer is correct. Yes, by Jensen's inequality and applies the fact that function f is convex. Yeah, excellent answers. Then clearly, like by Jensen's inequality and the fact that f is convex, then we know that the x bar is a solution that has a suboptimalities that are better than the average suboptimality of everything. Okay. So you can also prove that the average version of the solution when the function is strongly convex converges at the order of 1 over k with this additional log k. Okay, so this lines of research on understanding averaging schemes of stochastic gradient methods or stochastic subgradient methods, like, is surprisingly recent, right? So you would think of these methods to be around for a long time. It starts from 1950s, and in surprisingly recent literature, usually among the machine learning literature, are where people actually look into the more detailed analysis of this algorithm. So in particular, like these groups of people, they study the problem whether this log k factor can be removed if you construct the averaging schemes in slightly different way. So they showed that there are examples where this x bar doesn't really work. So you can't get rid of this log k in general, but suppose you use something else called alpha suffix averaging, which takes the nearest alpha proportion of the iterates and then do the averaging there, and then you can get rid of the log k factor and then get a concrete 1 over k rate with a universal constant. Okay, but this alpha suffix averaging defeats the purpose because it requires you to keep track of all the iterates until this point, rather than having this Polyak-Rupert averaging that allows you to keep track of the x bar without incurring additional computation. Okay, so this was solved like a year later by the same groups of author by proposing like an online update rule that implements something else that's different from alpha suffix averaging that's shown to be working. Okay, so so there are a lot of extensions. There are a lot of interesting theoretical work on understanding the convergence of gradient-based methods and stochastic gradient-based methods. That's even a very popular research topic as of today. Okay, and part of the reason of the motivation of these methods is by a very practical problem that we want to solve these problems for extremely large scale applications. So in practice, this averaged stochastic gradient descent actually works superbly well comparing to the standard SGD and comparing to other approaches that choose the learning rate in more and more interesting ways. Okay, so these two figures are coming from the popular paper by Leon Boteau, 2010. So Leon recently won the Test of Time Award, like for his contribution in rejuvenating the theory and practice of stochastic gradient descent and stochastic approximation from the 1950s. And the averaging scheme like was proposed but not analyzed in this work. But you can see from these practical experiments that running average SGD actually leads to significantly more stable solutions that gets to a lower objective function value a lot quicker than the standard SGD. Right? And the same phenomena occur in both the training and test error. Okay, so so the next question is whether this is the best that we can do. And whether the 1 over square root of k is really the best that we can do. We cannot improve it further for the family of problems that we're trying to solve. Okay. In order to see that, so let's introduce a more general family of problem called stochastic optimization or stochastic programming. So notice that previously we talked about solving optimization problems of this form. So minimize 1 over m sum of fi of xi from 1 to m, right? We talked about solving this kind of problems. As a matter of fact, so this kind of problem is a special case of the so-called stochastic programming when these are the expectation over a particular distribution, right? Over a particular uniform distribution over your data set. So stochastic gradient descent can also be applied to solve the more general stochastic programming problem where we do not really have to specify what this expectation is. Right, so suppose this is a population level quantity that we want to minimize, and all we have access to are samples from these distributions. Okay, if we can get samples f1 to xm that drawn from some unknown distribution, and then like maybe with that, like maybe even with just gradient access, maybe all we have access to are approximation to the samples of the gradient at these locations when we like provide a fixed input from some distribution in the gradient space, and potentially that's already enough for us to directly minimize the population level objective. There are more fancier versions of this stochastic programming approaches in minimizing an expectation and subject to an expectation condition, and then you need to solve this when all you have access to are samples. And you can also talk about the chance constraint stochastic programming in the form of you want to minimize an objective function subject to a chance constraint, subject that you want the probability of certain event occurring to be larger or smaller than some pre-specified value. So these are extremely useful in operations research and in business decision making, in deciding how much inventory to hold when there are uncertainty about your current model about what's going to happen in the future. And these are like hugely relevant also in cases like epidemiology forecasting, in projecting how long this COVID-19 situation is gonna hang around. Right? Because a lot of the things are stochastic and we don't really have access to the actual distribution, and all the distribution, all we have access to are samples from these distributions that occurred in the past. And the right decision, the way to do decision making are to solve these stochastic programming problems. Okay, so one particular example of the stochastic programming is say, well, let's like machine learning is the stochastic programming problem because we want to minimize the population level risk, while we only have access to the empirical risk. And in stock trading, in portfolio optimization, sometimes people talk about the bar or C bar, so value at risk or conditional value at risk, and these can be formulated as a stochastic programming problem with chance constraints. And how likely that if you invest according to this way of allocating your available resources, and the probability of having a single day drawdown of $1 million is smaller than 0.05. So this is like a more refined way of calibrating your risk, and then so you can do risk adjusted return maximization and so on. Okay. So why is this relevant to the optimality guarantees of SGD? So think about this problem. So SGD is such a general algorithm that can be used to solve like this style of optimization problem given stochastic gradient like oracles. So then SGD should be expected to solve this problem, like if we can prove the convergence of SGD with this family of problems. And these stochastic programming problems happen to be special cases of the family of problems where SGD can be solved, can be used to solve. right? So this is one example of that. It just happens that among these stochastic programming problems, there are ones that, like if SGD is able to go faster than 1 over k in a strongly convex case and 1 over square root of k in a non-strongly convex case, then that allows us to break the information theoretic limit. Okay, so here's the idea. So consider this stochastic programming problem, okay, where you want to find this parameter theta, this univariate parameter theta that minimizes that minimizes this I guess this objective function, right? And if you take the expectation over x, you can decompose it. So this is really the objective function that you can that you want to minimize. It's really simple, and we can calculate the gradient at any given theta relatively easily. But the point is that we don't really have the actual gradient, which looks like this. All we have is a stochastic approximation of the gradient in the form of a theta minus xi. So given n samples from this distribution, then we get like n unbiased estimator of this gradient. So this is the same information that's made available to us whether we observe the samples or whether we observe the gradients. Okay, but this is a statistical estimation problem. How we would construct the optimal solutions that minimizes the square loss by choosing the right theta, and we know that the optimal solution is achieved by choosing theta to be the mean of this distribution, right? So this holds even more generally than this simple example of IID Gaussian samples. So if we can solve the stochastic programming problem faster than 1 over n, with n iterations, with n rounds of then this is saying that even if we observe everything and all the information in the hindsight, and then try to construct this answer theta to approach mu as close as possible in the square laws, we can't really do that because this is a fundamental limit of statistical estimation, right? So this is coming from like the Cramer-Rawl lower bound or the minimax theory. This style of bound are called information theoretic lower bound or minimax lower bound, yeah, which says that minimum for all measurable function of your available data. And if you expect this to do well simultaneously for all possible parameters, then you can't. And this is always larger than sigma square over n, right? So notice that this is a one strongly convex problem. So stochastic gradient descent have a convergence rate of sigma square log k over m. K, and k is n and m is 1, so this is log k over n. So this is saying that the stochastic gradient descent convergence rate is optimal up to a logarithmic factor. Okay, and this logarithmic factor can actually like sometimes be removed to close the gap altogether. Like using a very similar argument, we can, I'm gonna skip these slides, but using a very similar construction by reducing to statistical estimation of Bernoulli random variables, we can show that in the non-smooth case, I guess in the non-strongly convex case, the 1 over square root of the 1 over square root of k convergence rate is actually also optimal. Okay, again, this is information theoretic lower bounds that we're matching, which says that it's impossible to get better than this for any algorithm. So not just those algorithms in the so-called Krylov space, as was established by Nesterov. Okay, so is this the end of the story? So far we've talked about how SGD can be extremely effective when you have a huge data set. We also talk about how SGD can converge very slowly as you approach to the global optimal solution, and how it cannot really adapt to the strong convexity properties as its gradient descent counterpart in improving the convergence rate exponentially. Mini batches, while popular, they don't really help that much in practice because it often takes the same number of flops or worse or more number of flops in order to converge to the same accuracy. And averaging trick will help to remove the log K factor, and it makes things a lot more stable, and that's the way to go in practice. But ultimately, it seems to us that it is really impossible to break the 1/square root of K like lower bound or 1/K lower bound for strong and convex functions. That's pessimistic, but recently there's some progress in this problem. It just occurred to people that there's actually a subset of the problems that are more relevant to optimization in machine learning called finite sum problems. So when this stochastic optimization problem's integral or this expectation satisfies that this probability is over a finite set, then you can actually often exponentially improve over the performance of the naive stochastic gradient descent. So there are actually algorithms that solves a subset of the problem that satisfy the finite sum exponentially better, and then it gets a benefit of the exponential convergence when you assume a strong convexity and so on. So hopefully towards the end of the classes, towards the end of this quarter, so there will be a advanced topic lecture where we talk about one instance of this approach that use variance reduction to achieve linear convergence rate for SGD. Okay, so I'm gonna wrap up. So SGD, like by giving some pointers to some of the more recent references. So SGD has really taken off in large scale machine learning as it's motivated by its appealing nature in solving both convex and non-convex optimization problems at scale. Like the improvement is really orders of magnitude without SGD. So machine learning and AI won't be at its position today. Okay, and the pioneers of deep learning people, their contribution, like essentially their early contribution is to show that how do you implement stochastic gradient descent for say a deep neural network using backpropagation. Okay, so there are many ways of choosing the learning rate. There are fast gradient methods, but there are also families of methods that connect between the theory of optimization to specific considerations in systems. In particular, this mini batch, like if you choose a mini batch, just as large as your GPU's memory the GPU's graphic memory can fit, then that might give you the best benefits in practice. And how do you take into account of the cache efficiency? And how do you deal with distributed optimization when the data are stored on different servers and you have to somehow communicate? And how do you minimize the communication costs? So things like asynchronous SGD would analyze problems like, what if your gradient updates are coming from servers that are pretty remote, and due to the latency, then the gradient will be calculated from a previous iteration. Would that also work? And sign SGD are something like you are quantizing the gradient or the stochastic gradient into just bits rather than the floating point number. Will that also work? So these are some of the more modern extensions of stochastic gradient descent that are more relevant to practical research, and it is still going on and on and on. There are hundreds of papers per year on these topics. So I'm gonna skip early stopping and jump to the very end. So I'll make sure I talk a little bit about early stopping and this interesting connection to statistical estimation with the regularization path at the beginning of the next lecture.